All right, so welcome back. Welcome back to this channel. So in the last video, we have covered a paper on application of stable diffusion, video generation, mainly video generation, not that related to stable diffusion, but mainly focusing on text to video generation. In this video, we are going to cover a relatively new paper, 17th March 2023. I wanted to read this paper for a long time, but I got the opportunity to read it and found it, found the details pretty, pretty simple, and I just want to share it through this channel. So I thought of making this video. Tune a video. The paper name is Tune a Video, one shot tuning for image diffusion models for text to video generation. So the idea is, you don't train the model, you just tune it or upgrade it from a text to image model to a text to video model, just like a little bit like the last video. We just upgrade it. We'll cover the details in just a minute. So this is the paper. This is the title of the paper. These people here wrote the paper from National University of Singapore and ARC Lab, Tencent PCG, School of Computing, National University of Singapore. So I think we'll dive through this paper. So this is the example. So the idea is, so given a video, in the inference time, or not the inference time, we can fine tune our model. So before tuning, we'll provide the model with a video like this, and we'll provide a description. We'll essentially provide a video and text pair, only one pair. We only have to provide like one video and one text, right? Pairing text, and then we could provide a input text. So after fine tuning it, so we'll provide this and we will fine tune our model. After fine tuning it, in the inference time where we are using the model, we could just provide the model with this description, with this title. Let's say James Bond is dribbling a basketball on the beach. So given this, we will use a pre-trained text to image model, and we will perform some operation. We'll cover that in just a minute. So we'll perform tune a video, right? And then we'll magically get this video. So again, the model already knows how things look like. So it actually learned how things would look like, and based on the video input video, before fine tuning it, we could actually the model will understand how videos work, and especially that video, and it would provide a video for us. It will generate a video, and then we could do that same for like different examples. An astronaut is dribbling a basketball, cartoon style, and you will get this good video. And you could also try like a prince with a shining crown is dribbling a basketball, modern Disney style, and you'll get the video. And then Iron Man is dancing on the beach. It does not only have to be like basketball. You could also like put in like these conditions. So rather than just you could input the text, and also with the text you could input like a sequence of actions or video, and the model will generate the given output after fine tuning it. So this is the model. One shot training. Will be performing one shot training. So yeah. So we'll just read the abstract. So, okay, to replicate the success of text to image generation, recent works employ large scale video datasets to train text to video generators. Despite their promising results, such paradigm is computationally expensive. In this work, we propose a new T2V generation setting, one shot video tuning, where only one text to video pair is presented, right? We only need one sample, right? We only need one pair of video and text. And then our model is built on the state-of-the-art T2I diffusion models, pre-trained on massive image data. So as I've told, we'll be using like pre-trained large diffusion models. We make two key observations. T2I models can generate still images that represent verb terms. Extending T2I models to generate multiple images congruently exhibit surprisingly good content consistency, right? We could actually use it to generate multiple images concurrently, and diffusion models does work for that process, right? Because there will be some type of similarity between different sequences, and diffusion is actually good at similarities because it has to subtract less. So it is subtracting the noise, right? They work because diffusion models work. We use it for image generation, right? To further learn continuous motion, we introduced tuner video, which involves a tailored spatio-temporal attention mechanism and an efficient one-shot tuning strategy. At inference, we deployed DDIM inversion to provide structure guidance for sampling. Extensive qualitative and numerical experiments demonstrate the remarkable ability of our method across various applications. Right. So the idea is, so we'll use the T2I pre-trained model for generating images, congruent images, and then just like we have like looked at the last paper in Maker video, we'll be using spatio-temporal attention. It will be using that attention to get the motion, right? I understand the video, how a video actually works. To learn that continuous motion of the video, we'll use the temporal attention mechanism, right? And then at inference, right, we employ DDIM inversion. So we'll essentially invert that image. So we'll essentially creating noise. I'll cover that also in just a minute, to provide structure guidance for sampling. So when sampling, that will provide guidance. So based on, so as I've told you, we'll provide a video and text sample, right? Before fine tuning. After fine tuning, we'll provide the text description, and then it will actually work. So I'll just show you an example I have here. All right. So we'll first yeah. So first we'll provide this input video and then this text. And then in the inference time, we can only we could provide this description, this text description, and the model will output this image. So the like the patterns is actually followed here also, right? So this is the content, the actual content, what is actually happening is followed here. But the but we are doing minor changes, right? So that changes is actually done by the model. So we'll be performing DDIM inversion to actually carry that content, carry that motion throughout the output video also, right? Let's go through it. So this is the this is a like pretty good diagram to understand what happens before like training and testing phase or inference time. So we'll be providing an input video, and then a text description. So only one pair is needed, and then we'll be creating, we'll essentially be transforming this text to image model to a text to video model, right? We'll be training it, we'll be fine tuning it. We'll be fine tuning a text to video model from this text to image model. In the inference time, we can just use this text to video model to take in like some description and then replicate it, but with the content that is present in the input video. So that is the idea of this like fine tuning. So this is the much better diagram to understand what is actually happening every year. So so this is the fine tuning and this is the inference time. So in the fine tuning, while fine tuning, we'll have the video and the text description. So this is the text description and this is the video. So what we'll be doing is we'll be adding some noise, just like in diffusion. We'll be adding some noise, and then we could actually pass this through a unit, right? Just like we could just pass that through a unit in which we have residual connections and so on, right? We'll be having a unit to regenerate it, right? And then we'll also be performing spatio-temporal attention. I've covered spatio-temporal attention in the last video. We'll go through that also pretty briefly. And then we'll be performing cross attention between the video and the text data, right? And we'll also be performing the like temporal attention, right? Between different types of, or between sequence of frames, right? So essentially, right, we'll be having a video, right? We'll be having some text, right? We'll be taking this text and using it for cross attention, to perform cross attention. And then we'll be taking this video, we'll be passing through a diffusion model. And essentially, we want to reconstruct this base video. So we'll essentially understand what is actually happening inside this like video to actually understand it. And then we'll be having like bunch of neural networks, attention layers also to understand the content of the video and about that video. And then and then after that, we will have like reconstruction loss. We'll try to reconstruct this video. And then and you could notice that bunch of blocks here are frozen, right? Will Much of blocks here are actually frozen because we like I'll cover that. I'll cover that also. Why we are frozening some blocks. I mean, reducing computational complexity is also one cause, and even updating them will not be a huge difference. I'll cover that also. And then so this is the fine tuning phase. We'll just fine tune this model based on this videos. Again, we are not only performing diffusion for like single image. We'll be performing diffusion for multiple for all the frames. We'll be taking all the frames, essentially images inside that are containing inside the video. We'll be adding bunch of noise, right? And we'll be passing them through this unit and try to reconstruct them, try to predict the noise, what noise is actually added to the model. And then we'll be performing this also, this self attention and cross attention and temporal attention, spatial temporal attention. In the inference time, we're going to take this input video that we already have, right? We'll be performing DDAM inversion. We'll be essentially converting this like noisy changes, also all of the changes that are happening. So we'll be taking we'll be we'll be adding some noise to these images. That is a very good term. We'll be adding some noise to actually see how the image changes, how the noise changes. And given this to this model, so this is essentially our model. So this is the input, right? We'll taking the noise and regenerate this image. We'll be taking this noise, and then we'll be also taking this. We'll not be taking this text, but we'll be taking this text inside our model and generate an image or generate a video, right? So then therefore we could actually generate a video like this. So that is the overline of the architecture, what the architecture actually is. You can actually read it. So given a text video pair, example, a man is skiing as input, our method leverages the pre-trained T2Y diffusion models for T2V generation, right? We'll be using this pre-trained model. During tuning our model, we updated the projection matrices in attention blocks using standard diffusion training loss. During inference, we sample a novel video from the latent noise inverted from the input video, guided by edited prompt, right? We'll be using this edited prompt, new prompt as a guide. And then we'll also be sampling a novel video from the latent noise. So from the latent noise derived from the video, after inverting the actual video that we provide, we'll get the latent noise and we'll pass that through this model. And also this prompt, which is Spider-Man is skiing on the beach cartoon style. So we'll pass that also. And that is the idea. So this is and we'll also be using spatio-temporal attention, right? So this is spatio-temporal attention. So we'll be taking one frame. So this is, let's say we are currently in ZVI. So this is the current frame photo, right? We'll be taking the past 2 frames or past n number of frames or whatever 2 frames, any 2 frames from the previous frame. So we'll be taking 2 frames before the current frame, and essentially we'll be performing attention. We'll be performing attention between this. And remember, we will not be updating WV and WK, and we'll only be updating WQ, right? Again, remember attention, right? So the formula of attention is like softmax of, I think we have used the same thing, right? Yeah. So we'll essentially be performing attention. Yeah. So this is the thing. We'll be taking Q times QT, Q times KT, and then by root D times V. So essentially, after performing WV, we'll be multiplying that by this image. We'll be taking WK and multiplying that by this image. We'll be taking WQ and multiplying that by this image, and we'll get the QKV vectors, and we'll be performing this function to actually calculate the attention, or calculating the relation between between these frames, essentially the query frame and the key and value frames. Right? By doing that, we'll do that for all of the frames, right? We'll be doing that for all the frames, and so therefore we don't have to update these weights. We only have to update this one such that we calculate the right attention, and then right, and we can also reduce the computational complexity, I think. Yeah. So these are some examples. A man is skiing. So this is the actual video, actual description, and we could actually change this description by a lot and get pretty good results. Right? Car is moving on the road. Actual video. We could actually change this description to get pretty good results. And these are some experiments, I believe. An astronaut is skiing on the moon, and we're getting some very good, pretty realistic images, and it is actually quite amazing and quite quite remarkable, the journey of AI understanding videos and images. Right? Yes, that's it. That's it for the paper. I'll just show you through the implementation, how the implementation looks like. I'll just right. So we'll just go through implementation. I think the official implementation. We have the official implementation. I actually thought of implementing this from scratch. But there is no time. Due to lack of time, I did not implement this from scratch. So I'll provide the link of this GitHub repository in the description. Make sure to check that out. Right. I think this is the official implementation, I think, and I just found it. So we'll be going through that. So these are the folders we have. Not like, it's not a very huge and messy implementation. Like if you look at a lot of implementations of huge models of research papers, you'll have many messy folders and many more subfolders and all that. But this is actually pretty clean implementation. So we'll go through this file first. I also haven't read the code completely. We don't have to read the code completely. Just understand the main parts is enough, I think. Yeah. So these are the main functions, I believe. Yeah, we'll be importing them from Tuna Video. I think it's a folder. Right. So we have the Tuna Video folder. We'll be importing many functions from that. Right. We'll be importing UNet. I think this is a training file. We will also train the text image model, I believe. And also we have the data set. We'll also import the data set, I believe. And then we also have the pipeline. I think the pipeline is the main thing that we have to focus on, because the pipeline is actually what we do with each of these models. We already know what each models do, the architecture of UNet and all that. And then we'll also use transformers to get the clip text model, clip tokenizer, I believe, pretty trained. We'll also get the DPTPM scheduler, DDIM scheduler, autoencoder. We'll get the autoencoder. Right. We'll be importing Torch. I think I think we'll just go through the Tuna Video. We'll go through Tuna Video. We'll go to pipelines and pipeline tunavideo.py. I think this is the main file which we have to read. I'll just cover the main parts. I'll provide as much context as possible for you. Make sure to read it by yourself also. I'll provide the required context. Everything that you need to know, I think I'll provide that. So I think this is the main class, Tuna Video pipeline. So we'll be inheriting that from diffusion pipeline, from diffusers. Right, we'll be inheriting from that. We'll be using the functionalities of this class also. That is the main idea. And then these are the inputs. these are inputs we'll be accepting. The VAE, which will be autoencoder KL. So if no VAE is like inputted, we'll be using this pre-trained model, I believe. The unit, the clip text tokenizer. All right. I don't think we need to care about all of this. We don't have to. We can just skip it. Skip it. Yeah, this is the encoder. I think we use it to encode the prompt. We'll be using the tokenizer. We'll be passing in the prompt, the padding, the max length, the truncate, like the truncation equals true, right? And then we'll be passing that to a text encoder, like self.text encoder, whatever that is. If you do not actually put anything, it will be the clip text encoder, the pre-trained clip text encoder, and we'll also be adding attention mask, right? I hope you know about attention mask to actually mask the next values to make sure the attention does not like cheat, right? While generating the next data, right? We'll be passing that to a text encoder, and we'll be passing the attention mask also, right? And then I will be passing that to a tokenizer. So this is the unconditional input. I think where is the unconditional input? Yeah, so this is the unconditional input. Get unconditional embeddings for classifier free guidance. We'll be performing classifier free guidance. I hope you understand. I hope you know what classifier guidance free guidance is. So essentially what we'll be doing is, right, while training a diffusion model, we will take the prompt, right, we'll encode it to embedding, right, rather than just passing this encoder embedding to the model to generate a text or to generate an image. We'll also be passing a let's say empty string. We'll be passing this empty string to a text encoder. We'll be getting the output, and we'll be adding both of these values and passing them through the model, and we'll get two images, one for the conditional input and one for the unconditional text. And then we'll be getting a weighted average between both of these, controlled by a hyperparameter, I think guidance scale. And then we'll get the final image. And the idea of using this classifier free guidance is for us to actually control the amount of obedience. So there will be a trade-off, right? Obedience and creativity. If the obedience is a lot, if the model is very obedient to the prompt, then there will be less creativity. And if there's more creativity, then the obedient to the prompt is very less. So we can actually control that using classifier free guidance. Right? We'll be taking this empty string, we'll be multiplying that by batch size. So we'll be essentially having multiple number of empty strings, and then we'll be passing them through the encoder. We'll be passing them through the encoder, the unconditional tokens, and then we'll be getting an output. And then yeah, so that's it. That is for text embedding. And then we'll have decode latents. I think we don't have to learn. Yeah, we'll be using the VAE to decode these latents. Essentially, that is I think the main function of this. The main advantage of this function, or the main use of this function. Right, I think right. So we have so after we'll just encode the input prompt here, right? We'll be preparing the latents, self.prepare latents, and then we will be I don't know, let's see where they are used. They are like the model is actually used. Let's see where the unit uses at least. Right, so will be yeah, so this is the we'll be passing them through the encoder, right? We'll be using doing classifier free guidance, and then we'll be having a tokenizer, right? And then we'll be decoding the latents, right? We'll be using a VAE, and then check inputs, prepare latents. So prepare latents, what we'll be doing, we'll be getting the shape, will be if instance generator, raise value error. If latency is none, that will be all right, all right. Then so this is the main function. So this is the call function. When we call it, this is, I think this is the main function that will be running. So yeah. So we'll be getting the height, the width. We'll be using the check inputs. Raise error if not correct. If the if this is not actually inputted, the prompt, the height, width, then the prompt, the height, and the width, right? Classify free guidance scale. So we'll be using that to get the guidance scale, and then we'll be encoding the prompt. We'll be taking this prompt, and then we'll be encoding it. We'll be calling that function, right? And then we'll be getting the number of channels and pass that through this function. Prepare latents. All right, we'll be passing that through prepare latents. Let's just see what that is. Prepare latents. All right. So right, we're going to pass that through this latents. We'll be getting the latents, and then we'll be calling this function prepare extra step. And then yeah, we'll be calling the unit. We'll be finally calling the unit on this noise, the latents. Latent model input, which will be the latent, the noise. We'll be taking the time step. The encoders will be taking the text embeddings, and we'll pass that through the unit, right? If classifier free guidance is true, then we'll be taking this. So we'll be essentially be dividing this or adding both of these values. Dividing both of these values. We're taking the noise prediction and divide both of these. Divide that into unconditional input, unconditional output, and conditional output, and we'll be getting and we'll be doing this formula, weighted average formula, to get the final image, right? So that is the idea. And then after I think after post processing, we'll be decoding the latents. Again, remember that we are whenever we are doing stable diffusion, we will not deal with direct images. We'll be dealing with hidden representations. That will be using the autoencoder, right? We'll be using autoencoder to decrease the size of these images, right? And after that, we could actually decode the latents using the VAE. We'll be calling that function. And this is the idea. So this is the idea of this is the overall pipeline of whatever is happening. I've covered that in the theoretical part also. Now let's go to models, right? We don't have to cover this also. The unit, right? The unit will be having a unit in which we'll be defining like bunch of, you know, like just CNNs, right? We'll be having bunch of CNNs and bunch of resonate connections. Yeah, we'll be having bunch of CNNs, and then so you get the idea, right? We have the unit, we have the resonate. Just I think just a bunch of CNN functions with residual connections, with a bunch of hidden states and all that. The attention, we'll be creating the attention also, right? We could actually use the multi-head attention function if they've used it. Yeah, we have, yeah. From the diffusions, we'll get the cross attention feed forward layers, and then we could actually use it in the model. And now, I think we could get to the notebook. We'll go to the notebook, what that is. Maybe let's see. Right, so tune a video. I think we could just use it for inference running it for inference, right? Iron mass keying, we'll get with the prompt, and I think we could actually run it. I think we could run it. Maybe we could. Right, so yeah, we'll essentially be calling that functions, the pipeline. We'll be calling the pipeline. And then I mean, you could download it. You could download this notebook and run it on Google Colab also, or even your own computer, maybe on Visual Studio Code. And then yeah, that is Tuna Video, another application of like diffusion models for image video generation. So thank you for watching, and I'll see you in the next video. So bye.